Okay, so I shared with you a paper about the project. I'm assuming that everybody went through it to be familiar with the work that I'm doing.
Yes, sir, I've seen the such paper.
So did everybody go through the paper, the conference paper that I shared? Okay. Um, so I will just go over the work that I'm doing right now in my research, and then after that we'll discuss some gaps or some other things that I'm trying to achieve in the same research. Um, so if you are able to read the conference paper that I shared, it's about a novel small-scale non-orthogonal multiple access communication technique using auxiliary signal superposition. So I'm assuming also that all of you are familiar with these terms, like for example, NOMA, which is non-orthogonal multiple access communication. But I will just introduce it as right now, introduce a general picture of the project that I'm working on. And then we will then talk about how we're trying to use AI or deep learning to enhance the efficiency of that particular system that we're designing. And then hopefully from this, you'll be able to get some ideas from the gaps that we're going to discuss, we're going to see on this project. We'll be able to maybe get some ideas that you'll be able to do as your project and get your project proposals. So let me just give you a small overview of NOMA, because this is important for you to be able to understand why we're doing this. As a researcher, it's always important for you to know the literature. First of all, you have to know the literature and know what is out there and what are the gaps, what are people trying to do, so that you'll be able to contribute something that is on demand. Because if you're not able to produce to contribute something that is on demand or something that you'll be able to sell to people, then you simply don't need to waste your time in doing it. So it's very important that the first thing you do is to understand what is in literature and know the question that the relevant question that you need to tackle. So right now we're going to talk about NOMA, what is non-orthogonal multiple access, which is on the in literature, and see what is on in the literature and see how we're going to improve that, how we are improving that in this particular project that we're dealing with. So non-orthogonal multiple access basically its main idea is many users more than available resources. This means basically that we have many users, but we don't have so many like resources. So we share them. We share the resources that we have with with the users. Why is this important? Right now, everybody knows about Internet of Things or Internet of Everything, where we are going to have so many things connected to so many devices connected to the network. We're talking about smart houses. We're talking about smart vehicles, smart meters. All these things they're going to be many in terms of millions, but we don't have resources to support all these things. So we're using non-orthogonal multiple axes to multiplex the resources that we have so that the devices are able to share these resources and so that they'll be able to communicate. So NORMA, which is on literature right now, downlink NORMA, for example, downlink power domain NORMA, looks like this, where you need to pair two users, one who has a bad channel and another one who has a good channel, and then you allocate them different powers, and then you're able to send your signal. When you send your signal, the user who has user one here who has a good channel, first of all decodes the information of user two, and then decodes its information, and then send it, and then this user decodes its information directly without decode by considering the information of the first user as noise. So this is a current normal which is there right now. So as I said, why do we need NOMA? Why is NOMA important? Because NOMA has high spectral efficiency, has high low latency, and improved coverage, and also massive connectivity. These are terms that you need to know. So all those are important qualities for Internet of Things, and well, 5G plus era. 5G is over now. We're talking about 6G now. So just to move on, actually let me maximize this. So what is now the main challenge in NOMA? The main challenge in NOMA? The main challenge is basically we have, for example, internal and external eavesdropping, which is security. Why do we say that? Because user, as I told you before, user one, first of all, decodes the signal of user two, and then user two is able to decode the signal of user one. I mean, its own signal. So basically here is the security. The security is a big concern when you are using conventional NOMA. Also, we have degraded bit error rate, BER, in the conventional NOMA. So this is also another challenge. So power domain NOMA, also power domain NOMA, which is the current NOMA available in the literature, has been rejected by 3GPP as a work item due to performance issues. So as a researcher, basically you can see that there is a gap that needs to be filled. We need to find a new communication technique which will be able to support, millions of things and also 6G devices. So as a researcher, you'll be able to see that gap, and now you'll be able to find ways of solving this problem. So also we have another thing that we can discuss, or another gap that we can see. We have cryptography. We need to see if we can use cryptography or physical layer security. Cryptography is a very common thing right now, which is being used in basically all, most, if not all, the devices, which basically means that we have key sharing, public key sharing, and secret key sharing, such that if you want to send information from a transmitter, for instance, Bob, to a receiver, Alice, you need to encrypt your data using a public key or a secret key, and then send your data. So this is not good at all in future wireless communication, because security is not really guaranteed in this case, because right now we have supercomputers which are able to basically find this secret key by brute force. It's just a matter of time. Whereas physical layer security, on the other hand, does not need key sharing. Physical layer security basically utilizes the noise and the channel randomness and interference to essentially protect the data of the user. So, and also another big advantage is that it does not require any processing at the receiver. Why is this a big advantage? Because in the next generation of like Internet of Things, we want to have as less processing at the receiver as possible, because the devices, there are small devices, they're supposed to use more power, they're supposed to have less memory, they basically have very limited resources. So we are trying to remove any kind of processing from those devices, from those receivers. So this is another gap that you notice, and you try to work on finding a solution. So basically, in a nutshell, we talked about this is secure communication. It's a major drawback in, for example, in the current Internet of Things. We also talked about cryptography is not desirable for Internet of Things 6G or 6G era. And we said that NOMA has shown great potential to be a communication technique which can be utilized in in this IoT 6G era. We also talked about physical layer security has a great potential to provide security for these devices with limited processing. All right, so now let's talk about the proposed method. Since we've now seen that we have gaps to fill in literature. So now let's do some research and try to find a model that we can propose that will be able to answer this question. So the model that we're going to propose is an advanced normal technique, which uses physical layer security to protect the information of the users. So let's say, for example, in this particular system, you have two users, user one and user two. And in the presence of an eavesdropper is basically a hacker who's trying to get information from information intended for user one and user two. So what we do in this particular model is we get the information that we need to the information for user one and user two, and then we transmit it in rounds. We say we first of all transmit the information in round one, and then we also transmit it again in round two using two antennas. Each antenna, one antenna is active, the other antenna is inactive. And then if, for example, antenna two is active, antenna one is inactive. And then in the second round, antenna one is active, antenna two is not active. So how do we send this information? We calculate auxiliary signals, R1 and R2, which will be sent in round one and round two. So R1 and R2 are calculated by considering the user channel. We basically calculate it using by looking at the channel of user one and user two. We calculate it in such that when we send the signal without any processing at the receiver here, the user one and user two is able to clearly get the signal intended for them. Like for example, user one is able to get this signal intended for user one without doing any processing at the receiver, without doing any decoding. And user two is also able to get the signal intended for user two without any processing, while the eavesdropper is not able to get any information because of the auxiliary signals that we calculated R1 and R2. Okay. So let's talk about the novelty of this particular system. So what are we basically introducing in this system? What is really good about this system that you're proposing? We have physical layer security against internal eavesdropper, first of all. And then we also have physical layer security against external eavesdropper. And then we have eliminated signal interference cancellation, which reduces complexity. Signal interference cancellation is basically used in the conventional normal, power domain normal, the one we discussed before. They are using it in the receiver to decode the information of, or to basically remove, to cancel the interference. We have also introduced a two-round transmission and also symbol auxiliary signal superposition for Internet of Things devices. So these ones are this is the math behind all this particular system. I'm not going to go deep into details into these ones because I trust that you've read the paper, you've seen the paper, and basically what we have is you have your received signal and you have your data here. This is your channel and this is your noise. So now I'm going to go to this part here, where we are going to calculate, we are going to see how do we get our R1 and R2, because now these are the important things. R1 and R2 are the auxiliary signals, the ones which we were superimposing on transmission round one and transmission round two. These are basically the ones which protect the user signal. So as I told you before, R1 and R2 are calculated by considering the channels of user 1 and user 2. And this is the total received signal at user 1, and this is the total received signal at user 2. So if you look at the total received signal at user 1, you see that from all this equation here, which is basically found by following the procedure from previous equations, you see that this part is the desired term for the receiver, for user 1. And all other terms are not desired. So what do? We set all the other terms to be equal to 0. And then if you look at the total received signal at user 2, you would see that this one is a desired term here, and the rest of the term are not desired. So we also set them to 0. Then using now this equation 1 and equation 2, we calculate our R signal. We'll calculate our R signal this way. So this is how we calculate our R signal. And by doing that, we get let's discuss some results of this particular system. We see that we have the bit error rate of user 1 and user 2 here. And then we also have the bit error rate of internal and external eavesdroppers here, where you have, for example, the bit error rate of user 1 listening to user 2, which is an internal eavesdropper, and user 2 listening to user 1, which is also another internal eavesdropper. Then you have Eve listening to user 1, which is an external eavesdropper, and Eve listening to user 2, external eavesdropper. And you can see that all the eavesdroppers are basically have the worst bit error rate, which means they cannot in any way get the information intended for any of these legitimate users. And you can also see the conventional norma that we talked about. We have, in conventional norma, we pair users, far user and near users, a user who has good channel and a user who has a bad channel. You can see that this is their performance. And you can see that the performance of this proposed model is much better compared to the performance of the conventional norma. So you can, in this graph alone, you can see that what we actually proposed, or the system that we actually proposed, has big advantages compared to what is found in literature. And this is the goal of every researcher, to try and improve to what is there in literature. So from this graph, you can see that we have made significant improvements to what is available in literature. And you can also, here you can also check the peak to average power ratio of the proposed model and conventional normal method. You can see that the proposed model shows shown in red and green here is better, providing this peak to average power ratio. Peak to average power ratio is something very important in communication because it leads to better spectral and energy efficiency. This is also a very big different, a big problem which is faced by OFDM systems. And our system here that we proposed and designed solve this problem by providing a smaller peak to average power ratio. Okay, so now let's get to AI in wireless security, or how the main question that we ask here in this model. This is now what I'm trying to work with right now. I mean, trying to find a solution to. So we're trying to find a solution of how we can integrate AI with the proposed model, or with the proposed model, so that we can make it more efficient. So one way that we thought of is, what if we, instead of calculating our R signal all the time, instead of these equations, let me see if I can go back to it really quickly. Instead of these equations of finding R1 and R2, like instead of you using all this H all the time, calculate it R1 and R2 every time you need to transmit your signal, what if we can replace this with a neural network, for instance, a deep learning neural network? So basically what you need to do in that is you need to construct a neural network using LSTMs, generative adversarial networks, or variational autoencoders. And then basically train this particular network using your H and your output, which are R1 and R2, so that every time you want to transmit a signal, instead of you recalculating R1 and R2, you simply input your H and then you get your R. This is going to improve the efficiency of this particular system significantly. So this is one area that we are trying to see if we'll be able to integrate this model with AI. Another potential method is what if we can use, instead of getting our H all the time. H basically stands for your channel. We can also try to improve the efficiency of this particular system or model by trying to see if we'll be able to predict the channel beforehand. And this will also improve the efficiency of this particular model significantly. And we can also do that by using one of these LSTM or generative adversarial networks or variational autoencoders. So in conclusion, and also to just give you a brief overview of the future works, we talked about a secure, resilient, and effective low complexity communication scheme. And we also talked about how physical layer security is used to provide zero information leakage. And we talked about, we gave some simulation results that indicate a reliable and secure communication technique with low complexity for Internet of Things, and which is better than the conventional NOMA or conventional NOMA technique. And the future works include extending this particular communication system so that we have a system for more than 2 users, as well as we also want to utilize deep learning to increase the efficiency of this particular system. So that is the presentation. If you have any question about what we've talked about, you can ask me now. So do you understand? Hello?
Yes, yes, sir.
Okay, so is everybody still there?
Yes, almost everybody.
Okay, so I'm assuming, are we all familiar with deep learning or artificial intelligence and these LSTMs and generative adversarial networks? Are we familiar with these topics?
No, sir. I am not familiar with the, except the deep learning. I'm not familiar with the LSTM, JN, or BAE because I've just, started the lectures 2-3 days ago.
Mm-hmm. So wait, did you say you're familiar with deep learning?
Yes, I've just from the first lecture to 2-3 lectures, and I just read about the deep learning.
I see.
Mm-hmm.
What about others? Is anybody familiar with deep learning, AI, neural networks? How about neural networks?
No, sir.
Okay.
This is just the start.
Well, thank you for the presentation, and I believe you can talk to them about the details of the neural networks and the details of these algorithms. You may share with them the MATLAB codes you have implemented, you try to implement. You can give them these codes, and they can try to develop algorithms using these codes. So also you can give them some resources related to neural network, artificial intelligence, machine learning, these techniques that you are using in your research, so that they can learn more about them. But for the time being, I think it would be a great idea if you show them how do you get these results. Just, I mean, you can open your code and run it in front of them and get the results that you showed them in the presentation. Share the code with them, and then explain to them how are you trying to integrate it with AI. So you can get like learning by doing, not by explaining and presenting. Learning by doing. You just go to the real simulation environment, which is MATLAB or Python. Usually we use Python, we use MATLAB, and just show them an example of how we simulate the systems. Explain them the MATLAB code that we will share with them, the parameters, the inputs, the outputs, how to code, how to get like full understanding of what's going on, and then you move and explain to them how to write a paper, a research paper, like the one like this paper that you are presenting to them, starting from the abstract till the conclusion. How do you do each part? Because they are expected to write a paper, at least a good report. So these are the two tasks that you need to show them as well, so that, and I was expecting that you will share with them some ideas related to AI security, but as far as I can see, there are no new ideas. They are the ones that I just discussed with you.
Sir, can I ask a question?
Yes.
Uh, uh, in terms of artificial intelligence, sir, for example, there's Google Assistant, Huawei's Assistant also, and the Samsung and the Apple Assistant. You already know about them. So at the end of these whole programs, there is coding and programming. So what I'm trying to get from this presentation is that when we integrate this whole scenario, the NOMA, conventional NOMA with AI, so it's not conventional anymore, and the through PLC and PD NOMA. So here in this report presentation, there are only two users. So when we integrate with AI and improve this even further for more users, so I think there is going to be very interesting and unique programming which is related to performing arrays, automatic random selections, just like deep learning, for example, through deep learning.
Yes, actually, we are using AI in order to reduce the complexity of calculating the values we want to assign to the transmitted signals.
Hmm.
So this is the use case, but if there are other use cases, we also can do them as well.
Hmm.
Uh,
So by using
well,
AI,
well, yes,
I think by using AI, we reduce the complexity and the time consumption, which is in order to find out the everything. For example, the capacity, sorry, the channel or the auxiliary signal.
true. You are right, absolutely right.
Hmm.
And this is what we are trying to do here.
Hmm.
So
Okay.
we designed the system using math. Now we want to use AI, black box. So now Joel will open the MATLAB for you and show you the codes, explain
Hmm.
the codes to you and how he is trying to integrate AI. And these codes, you will have them with you by the end of this lecture and start looking, and your starting point are these codes. These are examples of how to build things.
Hmm. Okay.
Okay. So wait a minute. Just give me a minute. Okay, so these are the code um, for the system that we were talking about. So what is basically happening here is
We cannot see the code, Joel. If you can share with us the screen of the MATLAB.
you are not able to see them? Oh.
No, we just see the presentation.
Okay, wait. Now? Are you able to see now?
Yes, yes, now is fine.
Okay, so as we discussed before, in this case, we have we looked at, like, we have different channels for user 1 and user 2.
No, Joel.
Mhm.
Those are new students. They don't know much about how to simulate the communication system. So I would rather prefer that you explain things step by step, all the parameters starting from the first line.
I see.
You just, even some of them, they don't know MATLAB.
Okay.
This is example of how to simulate communication systems, and then you talk about AI role inside the communication system.
Okay. So we have our okay. Let me start from here. I'm trying to see how we'll be able to capture all the because if I go line by line, we probably will not be able to understand it well as well. So what we're trying to achieve is we want to send our signal, and the signal that we want to send it. Wait.
You know, Joel, the way you should explain it maybe is like this. The first, don't care about the beginning of the code. The beginning of the code is just defining parameters for
Yes.
some of the variables that we need inside our simulator. So skip until line 30, until this line 43, all the above ones are variables. We define them to use them inside the for loop.
Yes. Okay. All right.
Now the for loop starts here.
This is the
For each SNR, signal to noise ratio at the user, we also, there are variables that change within the for loop, and there are variables that don't change with the for loop. So the variables that change within the for loop, we put them inside the for loop. The other ones, we put them outside. And you start from here, and this channel is basically, you are defining the channel, the medium between the transmitter and receiver, and your actually transmission starts from where? From generating the random data bits. Where do you do that, Jewel?
here.
Here. So this is, you can link this with your system model, the picture that you showed them, the brief picture that shows how you added the signal.
Okay.
So you can link this code with that picture. You can go forth and back between these two frames, like one frame for the figure and one frame for the code, so that they understand the full picture.
Okay, just give me a minute on this.
Sir, can I suggest something, some idea?
Yeah, sure.
Yes, you can.
Sir, just as you said that even from some of us students, we don't know about MATLAB that much. So I was wondering, why don't we, after 3 days, have another meeting? In between these days, we students try to understand MATLAB, AI, and also take some lectures of wireless communication. So we at least have some ideas about the background and the overview of the what is actually going to happen if when we start the
True.
project.
In this case, you will get confused and you will waste more time. This
Yes,
is
sir.
not focused. You will learn MATLAB while you are trying to build your system. Don't worry about that. MATLAB is the easiest programming language ever. MATLAB and Python. So you will learn it while you are doing your project. Don't waste your time just going through documents and some other irrelevant stuff that it will waste your time and you don't need it. You just learn from your project. You learn from the things that you are doing. So learn MATLAB from this code, for example, the one that Joel will share with you. I know what you are doing. This is, we call it baby step teaching style. We are now master students, yes? Now, we learn while we are doing. The most important thing is to reach the goal. What's the goal? To implement something novel that can solve a practical problem. You come up with a problem and you invent a solution. To show, to validate your solution, you need to test it. Where do you test it? You test it in MATLAB. That's it.
Okay, got it, sir.
Okay, so as the professor said, everything before here, before this for loop is simply parameters that we use inside this for loop. And we have two for loops here. This for loop, this first for loop goes through every single SNR, which is basically stand for signal to noise ratio. For every single SNR, you need to do this. You need to transmit this number of signals. So for every SNR, you need to transmit this number of signals. And so for every transmission that you're going to make, you will need to determine this H. You need to find, as we can see here, you need to find all these channels that you're going to transmit it through. So this is what is happening basically here. We're finding these channels. You can see we have H11 here, H21, right, like here, H11, and we also have H21. This is from the first antenna. Then you see also that we have H12, and we also have H22 here. You have here you have where is it? So this is if this is this one. This is H32 and H32 and H31. So for each round, this is round one, we do this, we find these channels. So for round two, for instance, you find the other channels, H12, H22, and also Eve, like all these channels basically. So this is where we're finding it, round one and round two. And then now, after you do that, then now you need to find now your user signals. How do you find your user signals? You simply just generate random bits, because now you need to, this is going to be your user signals that you're going to transmit. So we generate them here, and then we modulate them, basically sending to, because before you send it, you need to send it by +1 or -1 in BPSK. And then this is now your user 1 and user 2 here, like these ones. This is user 1 and user 2 signal, X1 and X2. So when you have that, then now the process now of calculating R1 and R2 begins. Because now you need to calculate R1 and because now you already have U1 and U2, you already have this one, U1 and U2, you also have H1, all this H. The only thing that is remaining is for you to calculate R1 and R2. So this is what is happening. This is what is happening here. We calculate our R1 and R2 from this H, that we have. So we calculate it here. Here is just, here I'm collecting this data because now I need to train a neural network. And for you to train a neural network, you will need to have your inputs and you will need to have your outputs. So in this part, these are simply variables which are trying to collect that data to be used to train the neural network. So before you'll be able to use the neural network, you need to train it. So you collect your data here so that you'll be able to train your neural network later on. and put it to the channel data, which is the inputs. This channel data, sorry, these ones. You could collect all your inputs here, H11, H12, and also user signals. And then you also collect the corresponding R resulting from this particular RH. And then after that, now we do the transmission now, as you can see here. Now we do the transmission for each round. So our transmission, we said it's U1, user one, like you can see here, is this addition says user one data plus user two data plus auxiliary signal data during the first round. So during the first round, TX1 becomes, we have user one. This is simply, we are multiplying it with some sort of power. And then we say user one data plus user two data plus R, just the way it is here. We say user one data plus user two data plus R, plus R1. This is during the first round. In the second round.
Joel, can you
Yes.
show them the equation inside the presentation of these two line of codes?
For these ones, T1 and T2. So this is U when this is U1 and this is U2. This one, U1 and U2. What is U1 and U2? U1 and U2 is basically X1, X2 plus R1. And this is U1. And during the second round, we have X2, X1 plus X2 plus R1 plus R2, sorry. So, and then we're basically, this is basically what is happening here for U1 and U2. Okay. After that, we have this process here, which is basically a normalization step. And then we add guard intervals, basically to prevent interference. And then this is how we calculate our signal to noise ratio. And here, this is let's find this one here. Y11. Y1. This is this equation here, which says H11 U1 plus the noise. This is the noise, and this is basically how we're doing it here. We say TX1. We have our Y11 here, which is basically, which one? X1 here. So it's basically the signal we're transmitting during the first round, this one here, multiplied by the channel, and then plus the noise. Y11 plus, and then we also add the noise here. Then Y12 is this equation here as well. We do the same thing. And then Y2I is now for Eve, the same thing. For Eve, it's not here, but it's basically also the same thing, which says the user data times the channel plus the noise. So after you do that, now you have transmitted it through the channel. Now we need to remove our guard intervals, which we put recently, for you to be able to get Y11, Y12, and this one. This is basically now this one. Wait, not that one. Yes, for you to be able to get the received signal during the first round, for you to be able to get the received signal during the first round at user user one, this is the process of receiving it. And then for you to get the signal at transmission round one at user two, this gives you that. And then here, for you to get the received signal at user at the eavesdropper, this process gives you that. This was all during round one. So now we do the same thing. Now we change our transmission to do the second round on the second antenna. This was happening. All this was process of transmitting this data here from TX1 here. Here. So this was all this TX1 was for this particular first transmission. So now our Y11 here, our Y is here. At the end of it, this is you're getting because of the first transmission. Because of the first transmission. So now we go now again to TX2, which means we change now from this antenna now to this antenna. Okay, when you do that, we have now X2, which we are transmitting from this TX2. If you look at it here, we have now our R2 here. So during our second transmission, we do the same thing of what we did in the first transmission. We add our noise. This is our noise here. We add our noise, we multiply by our channel, and then we get to the received signal during transmission round 2 on user 1, Y12. And then during transmission round 2 on the second user. This is now when this one is active. We get this one. And then at eve, we able to receive our signal like this. All right. So how do we get our total signal now? Because we are transmitting our signal during different times, our total signal at user 1 is received by this process here by multiplying H11R, R1, and by simply summing this I received signal during the first transmission round and the received signal during the second transmission round. And then for for user 2, terminal user 2, how do you get your total received signal in the terminal 2? You simply sum what you had in the first transmission round plus the second transmission round. And for if as well, you do the same thing. Okay, so here, now that we have our all total transmission round, now we do demodulation. We demodulate now our signal, the signal that we received, to get the original data now that we transmitted. So you get this is your data received, and then your data received at user 1, data received at user 2, and data received at eve. And then after now you received your data, now we come here where we now trying to find our bit error rate. And basically bit error rate, what we're trying to find out here is how much information have we received, for example, in user 1. Is it how much information did we get exactly what we sent? So here what it does is you're taking the sum of see this X. This is basically how you do in MATLAB to see if this term is equal to this term, and this X this one is what we transmitted. No, this is the original data. If you see it here, all the way here. See, this was our data that we transmitted. Now we want to see if this data that we transmitted, how much of it is equal to what we received. How much is equal to what we received in user one. You see, this U1 is what we received. So this is what we transmitted. This is what we received. So how much is it? How much of it is equal? So we store it here in this particular variable, and we sum it all the time, because we're in this for loop, in the inside for loop, we are sending thousands of bits. So every time we go through this for loop, we calculate how many bits have actually been sent and have been received. And we do the same thing for so here we are calculating the bit error rate for user one. Basically, the data we sent for user one, the data received in user one. And then here we do the data received for user two plus the data that was sent for user two, where we also need to calculate the bit error rate for user two. And so here now we try and see what about the data received by user two, and the data sent by the data received by user one and the data sent for user two. So how much of user two's data has been received by user one, which means the internal eavesdropping now. Has user two been able to get data that has been sent for, has user one been able to get data that has been sent by user two? And then this is how we calculate here that bit error rate as well. And then here we calculate also, has the data that has been received by user one, is it how much of it is the data that has been sent for user one? Okay, so we're trying to see if user two has been able to obtain data that has been sent to user one. So internal eavesdropping as well. This is how we calculate it here. And then we calculate now external eavesdropping, where we say how we see the data that has been received by Eve, and how much, and the data that has been sent for user one. So how much of user one data has Eve been able to get? And this is how we calculate it here, by summing the bits in each iteration. And then we say how much of user two's data has been received by Eve. We're trying to see also if Eve was able to get data that has been intended for user two. This is how we get it here. After all that, we sum. At each iteration, we have been summing the number of bits that we've been sending, because we need to calculate. We need to use it when we are calculating our bit error rate. How we do that is, for example, you say, this is how we do it here. So for you to now to calculate the bit error rate, you need to say this bit error rate. For example, for user one, you say, okay, this is the number of bits that has been sent and received by that have been sent to Eve and that has been sent to user one and has been received by user one, out of this number of bits, this total number of bits that has been sent. So in that case, you'll be able to get what is the bit error rate of user one. And we do the same for bit error rate for user two, and then bit error rate for Eve, and bit error rate for and the bit error rate for Eve as well. So here this is now a different process where this is a function that basically taking the data that I collected. Remember the data that I was collecting here, this one. So that I'll use it to train my neural network now. I was collecting my channel data, and I'm also collecting my R data, so that I'll be able to train my neural network. But then before you train your neural network, you have to normalize your data. You cannot just train your neural network like that. You have to normalize your data. So this process data basically normalizes my data, and then it returns the channel data, and then it returns the R data, R1 and R2, and then returns the sigma and mu. Basically, sigma and mu are they are used for, we are going to use them for normalizing our data. And after that, now I need to train my neural network. This is how I train it. This is another function that takes in the channel data and the R data. When you take in the channel data and the R data, now it returns me a trained neural network. And this is basically I, which tells me how much of data has been used, so that I'll be able to use the other data the remaining data to test my neural network, to test the result that I've received. After that, now here I have a trained neural network that has been already trained. And then now I need to test my LSTM neural network. So I say my test, I simply collect, let me see. I select my X test and Y test, which basically means my input channel, my input data, which is the channel data and also the user data, and my Y data, which is my R data. And then I now put it in my trained neural network. This is how you just say predict. Then you put your neural network. This is your trained neural network. And then you put your X data. And then from that, you get your Y predicted. Okay. So once you get your Y predicted, you change it. Because now the Y predicted here, which you get here, is basically your R signals now, your R1 and R2, but they are normalized. So what you do is you denormalize them here. This is how you change them to like the original now predicted value. After that, you get your predicted R1 and predicted R2. This is just a debugging thing actually, because I'm trying to see if the data that has been normalized is the same thing. Basically, I'm trying to find out if my mu and sigma here are working well with this data. And after that, this is now where I simply plot my data. I plot my predicted R. You plot your normalized and the one that has never been normalized. So basically, I hope this was not very confusing. And that's the whole code. I think I will send this to you so that you'll be able to familiarize yourself and go through it again. And then if you have any question, just let me know.
Thank you very much for this. Now you can go to your paper and explain to them how you wrote it, section by section. How do you write it?
So the conference paper.
The journal would be better.
Okay. Okay, so first of all, I find it using LaTeX is usually like the best way, most professional way of writing your work. You don't have to use LaTeX. You can simply use this overleaf, which is an online version of LaTeX. And
We cannot see the screen again. I think you are sharing a specific screen.
okay. So this is the journal paper for that proposed system that we just looked at. So basically, the paper, a journal paper, has a couple of basic components that parts that it must have. You know, you must have an abstract, you must have an introduction, you also probably must have a literature review section, and then you also need to have like your body, your system model, and then if you okay, being a journal, you will probably be proposing some sort of new technique. So you're going to have also a system model part, and then you're going to have after you explain your system model, you're going to have a results section, um, and then finally probably you're going to have your conclusion. So those are just like the main parts of uh, um, a normal journal paper. So in looking at this journal paper, for example, in the abstract, the main things usually that this is like the main part that a reader or anybody who wants to read your paper looks at first. So in the abstract, basically what you have inside is you're supposed to have like the main idea, the main goal of your work. You also are supposed to have, you definitely need to have a section that is summarizing the results that you've obtained in your abstract. And so also we also have, you know, the index terms. These are also quite important because it's easy to find your paper when you like index couple of terms associated with the main idea of your work. And then inside the introduction, basically what I usually do for my case is you kind of have a narrow something starting from a little bit broader perspective, and then but not very broad though if it's a journal paper, and then you kind of narrow it down just to take the reader to, you know, be able to make him or her understand the main point of your work. Like for example, here you see I'm starting with Internet of Things, for example, which is a very broad topic. But then I continue with that, and for instance, here you see, due to its unique properties, I'm already talking about non-orthogonal multiple axis. I started with the Internet of Things. I'm now in NOMA, and I am giving the reader some trying to show him exactly what the gap is and what I'm trying to achieve. And after that, you need to have, in your introduction, you need to very clearly state the novelty of your contribution. Because if you're gonna write if you're gonna write a journal paper and you're gonna have editors who are gonna look at your paper, and the first thing they're gonna check is what is exactly your paper adding to the literature. This is very, very important part, because if it's not adding anything, why then should it be there? So in your introduction, you must address the novelty of your work. And then after that, after you address the novelty of your work, then the last section usually in the introduction is basically stating out, you know, the how your paper is structured, and how in each section what are you talking about in each section. And then after that, usually it's followed by a literature review, and try like here, for example, I'm giving a normal review so that the reader will understand, will much better, what that you've done, your literature, like you've read other articles and have seen what is needed, and how does your paper compare or with the particular literature that is out there, with other papers that are out there. How does your paper compare? So you address that by looking at other papers, other works that has been done, and then clearly stating that your work is different in a particular perspective compared to the works that you've read. And then after that, you now have your overall system model. You definitely have to have your system model. In your system model, you state you need to put your algorithms, for example, like you can see here, this is my proposed algorithm. You put all the details about your algorithm or the work that you're trying to propose. You can have some subsections, trying simply to explain how your work is structured. And if you're dealing with if you're going to have equations in your work, it's also very important to take a note of the very small things. Like, for example, you can say that if at every end of equation, if it's a part of a sentence, it has to have a full stop. Your equations need to be part of your paper, part of your sentence. Like, for example, this is a complete sentence here. You can see this is there's a comma here, there's a full stop here, because the equations need to be part of your work. You don't just put them just like that. They need to be part of your work. So these are some of the small things that reviewers take note and to see that if your work has been written professionally or not. It's also important for you to take care of for example, if you're dealing with matrices, if you're dealing with vectors, there's a specific way for you to write equation. There's a specific way for you to write a vector. There's a specific way for you to write a matrix. Like a vector, for example, is written with a bold when it's bold with bold letter, but it's a small letter case. Matrix is written bold letter, but capital letter. So these are some other things that you need to take care of. And after that, then after you've talked about your system model, then you come to talk about your performance analysis. This is a very important section as well. You need to talk about your performance analysis. You need to, here is where now you put your simulation results and discuss them in details on what is reflected by this simulation results that you've achieved. So you talk about your simulation results in your results method, and then finally you do your conclusion. And in your conclusion, basically what I usually do, there are a couple of things that you need to address in your conclusion. The first is you need to talk about what you've achieved in your work, what has been achieved in your work. And also, it's very important that you talk about your future work. You need to talk about what you're going to do next after, how you're going to extend your work or make it better. And then basically you're going to have your reference section as well. So yes, this is how I mostly write my work. Any questions?
So thank you, Joel, for the presentation, for showing them how to write a paper as well. Conference or journal, they are the same basically, but journal is more comprehensive. Now I just need from you to send them the codes and the LaTeX file of this PDF article. So if anybody has any questions to Joel, he can ask him.
Sir, are you going to share this recording as well?
Yes, we will share it. We will share it with you.
Hmm.
Joel, you can upload it to your Google Drive, get a shareable link, and send it to us.
Okay.
Uh, like and share with them the LaTeX file that generates this paper so that they can have it as a template and the codes and your presentation as well. It will help them as a starting point how to present your ideas and your work, and then they can start working on their ideas, like using different neural network structures to improve the performance of the current technique that you have proposed in your paper. As a like, let's consider this a training for you. There are no novel ideas here. You are training yourself. In this training, you will be learning MATLAB, you will be learning neural networks, you will be learning how to write LaTeX, how to use it, and then once you are comfortable with the programming language, comfortable with the topic, we can assign you a specific idea that you can implement and have a paper out of it.
Yes, sir.
Okay.
So I'll send you the link to this LaTeX thing so that you'll be able to access this. You'll probably just need to create an account.
I think, Joel, if you can download it and send it to the, okay, send them the link, but they will not be able to access the link except to read.
Oh, I see.
So it would be better if you download it as a package and tell them to create an account on Overleaf and then upload this package to their own account.
Okay. Okay.
Okay, then if there are not any more questions, if there are no more questions to be asked to Joel, then we can, I believe, stop here. We covered everything important that needs to be that needs to be done so that you can really start working on your ideas and in your projects. So, do you have anything additional you want to add, Joel?
If you have any questions, or any ideas you would want to run by me about your project, you can always write an email to me, and I can help you out in any way.
Very good, Joel. General advices to them, like to be a successful master students, hopefully to be like good researchers in the future, good inventors, good innovators, good engineers, good professors. Maybe some of them they want to be doctors, professors, whatever. Some good advices from you to them.
You basically have to put in the work and just do your part. And it may seem a little bit difficult right now, especially when you're just starting. But yeah, I promise you, it will get easier and it will get much more interesting. So you just keep working at it, and you have to try because so many people want to help you out. You have to take challenges. Like for example, the professor is encouraging you to learn neural networks. This is a very novel. I mean, not novel, but it's in everywhere right now. Neural networks. You need to learn how to program. If you don't know how to program in MATLAB, you need to learn how to program in MATLAB. You need to, so just take every opportunity as a learning opportunity and put in the work, and people are there to help you out. So that's just my.
Yes, sir. So you are going to share the video, the links, and the codes, and this overleaf.com website links, and the documents, account, all the things. So, sir, I was wondering, and after we receive this, when we start the, as the sir mentioned, the training, for example, this whole training, and after that, we are going to start get our idea, just like sir told us. So, sir, how much time should it should be, took we take? So we need to start our own project. 1 week or two. Can
Uh,
you explain that?
you need to get 1 week for the training, maximum 1.5, and by next week, by the second week, you must be working on your idea. Okay, so this week is gonna be like hectic. You need to learn all the things that Joel will share with you.
Okay.
Go over them, understand them, learn them, and then so that you can start. While you are reading and learning and investigating the code, you might come up with your own idea. What if we can do? What if we can add this? What if we can move this to there? It will maybe give us, it can improve the results. It can give us, but with logic, with sense, with meaningful statements, with meaningful motivation. So as long as, what do we search for as researchers, as a master student? We always search for problems. What's the current problem we have? Complexity and not very nice performance. So what we are trying to do is to reduce complexity, reduce delay, and improve the performance more. So you are clear about the problem, then you can think of solutions.
Yes, sir.
That's it. So I believe that's it for today. And Joel will be following up with you with emails. And in case you need any help, you can contact him directly. And especially regarding the ideas, it's very critical that everybody will be working on a very novel idea that can lead to a publication. You don't waste your time like doing something that can lead nowhere. Okay.
Sir, can you define a novel? I'm confused about this word.
Novel, something not done in the literature. Not you search on the internet, nobody has done it.
Okay.
Novel, this is what we mean by novel. You are the first one to do it. So basically you are going to go through something that there is nothing on the internet about it. If you are not reaching to that level, this means that you are not doing something new.
Yes, sir.
So the things that Joel presented, nobody has done them before on the internet. He was the first one ever on earth doing this. That's why we call it novel and publishable work. If there is another body who's doing this, or he has a paper similar to what you want to do, this is not novel. This cannot be published.
Yes, sir, I got your point.
Okay. Thank you very much, everybody. Thanks for joining. Thanks for attending. I hope now you are motivated. You are willing to work hard and become one of the most successful engineers in the world in the future. You can work wherever you want. So then we can stop here, I believe. I think we have covered all the topics we wanted to cover, and Joel talked about the important points. So, and since we answered your questions, we can just say bye-bye to you for now, and see you in the next meeting.
All right.
Okay, sir.
All right. Assalamu alaikum. Take care and stay blessed. Have a nice night.
Yes, sir. You too.